Oh, okay. Should start looking at multiple variables. Right? Okay, good morning, everyone. So let's start the morning session with the third lecture by Jose Gonzalez on studying varieties.
Thank you. Good morning, everyone. So let's start. Let me go here. Let's start recalling these procedures that we just discussed. One of them was to, starting from a cone, we have produced an affine variety, and then later, starting from a collection of cones that fit nicely, we produced an abstract variety. So let's review how that happened. So from cones to affine toric varieties. Our procedure was as follows. We started from a strictly convex rational polyhedral cone in Rn. If we don't ask for strictly convex over here, when we take the dual, what happens is that we see that the torus is smaller dimensional, so we are not going to get a variety containing the torus of the size that we want. So that's why we put strictly convex over here. You can, for example, think of taking your cone as the whole Rn and see what happens. You'll just get a point. Like the dual would be just 0. Then when you do the semigroup algebra, you will see that you get a spec of just a copy of the complex number, so you get a point which would not contain the torus. Okay, then starting from one of these nice cones, so polyhedral cone, so it has a finite set of generators, rational, meaning I take those generators with rational coordinates or equivalently with integral coordinates because I can scale. That's our first step, like starting point. We get a new polyhedral cone by taking dual. So we look at the dual Rn. For each point over there, we ask, hey, does this one do dot product with all my cones sigma greater or equal than 0? If it does, it is in the dual. And if it doesn't do that, then it is not in the dual. Okay. After that, so starting from sigma, we go to the dual. Then we look at the integral points in that dual. It gives us some semigroup, but actually, under these assumptions of rational polyhedrality, this semigroup is finally generated. Now, we can pass to the semigroup algebra. The finite generation over here, in the sense of a semigroup, is inherited by this one in the sense of a C algebra. So we have a C algebra that we can see lives inside the polynomial ring in as many variables as the dimension localized at the product of the variables, which is a domain. So this one is a domain that is finally generated as a C algebra. Then, using the correspondence between those and affine algebraic varieties, we get an affine algebraic variety. And then we discuss why it comes with a copy of the torus inside as an open set with an action of the torus on the whole affine variety, which extends the action of the torus on itself by multiplication coordinate-wise. So these ones are affine toric varieties according to the definition we gave. And let's see then the procedure. Starting from sigma, we said we go to the dual, intersect with the lattice. So we get the lattice points inside this cone. It's a finally generated semigroup. Then we get a finally generated C algebra that is a domain, and then we get an affine variety up to isomorphism. Very good. Then in a particular example, start from this cone, one can see using these inner pointing normal vectors that, maybe that's a little off, like this one and like this one, that this is the dual. Then we can see over here these lattice points inside, and you can see that you need these three guys to generate the semigroup, and those three guys work. So then we can map three variables x, y, and z on top of these points, and then it takes a moment to see that it satisfies this relation, and that is the only one. I think you guys work out this problem during the problem session, and then we take the associated variety to this, which would be just looking inside this one at the zero set of this polynomial, which would look like this. So this is what we have been doing from a cone to an affine variety that turns out to be a toric variety. Now, we did the same, but for a collection of these guys. So we take a nice collection of cones. We gave it a name, a fan. And then, how did that work? The cones are nice, meaning just as before, so they have to be strictly convex, rational polyhedral cones in Rn, and they fit nicely. What do we mean by that? If you take a face of any of them, which again is defined as you have some half space, such that your cone is on one side, and then the intersection with that boundary is precisely the face. That's how we define a face of a cone. Then is close undertaking faces. It's a finite collection of cones that are nice, close undertaking faces, and additionally, they are put together nicely in the sense that the intersection of any two of the cones in the fan is a face of both. And we drew before cases where it was not a face of both. We want like a face of both. Very good. So then, the procedure to get the abstract variety is as follows. For each of those cones, you follow the procedure in the previous slide, and then you get an affine toric variety. One shows like a small lemma saying, using some localization, that if you have two cones in the fan, one of them being a face of the other, like here sigma 1 is a face of sigma 2, then the corresponding affine varieties, one sits inside the other one, the smaller one sitting inside this bigger one, and as an open set. You get an induced morphism from one to the other, that one sees that is induced just by some localization at one element, so it lives inside as one distinguished open set. Then now, this allows us to glue all of those guys. How? If you have two of these cones there, you can glue these two along this common open set. So you glue them as topological spaces, but you see that the algebraic structure also glues. So you get some algebraic object that one can show is actually separated and has the normality assumption that we include in the definition, so it is a normal variety. And then, after having glued them like that, we went further and showed that the torus still lives in there because the inclusion of the torus on each of these copies is like compatible. So we get the torus on the final glued variety, and then we have actions on each of the affine patches that we are gluing, but those are compatible because like some diagrams that commute, that one can easily see that commutes because they are essentially used by inclusions, and when you include twice, it's the same as include at once. So you get the commutativities that you need to glue the action to have an action of the torus on the whole abstract variety that you produced, and it is normal, and then we have everything we need, and the action restricted to the torus, you can restrict in two steps using one of the V sigmas and then to the torus, and in the V sigma, the action restricted to the torus was the usual action of the torus on itself, so then we have the definition that we gave of toric varieties satisfied over here. That's what we have done up to now. From a cone, we get an affine toric variety. From one nice collection of cones called a fan, we get an abstract toric variety. Then let's look at some examples. Say that we have Zn. And in Zn, in the integers to the n, let's take the canonical basis. And let's define E sub 0 as minus the sum of all of those guys. We have seen this picture before. Let me do one picture over here. So this would be E1, this would be E2, and in this case, E0 would point like this, right? And then over there, these guys are telling us, then take the cones generated by all proper subsets of that finite collection of vectors. Okay, so what are we getting over here? Well, with some color that I can choose over here, this one is one of the cones, it's a proper collection. This one is another one, this one is another one, plus the 3 rays, and plus the origin. So those are cones over there. We saw this picture before, and then in this case over here, we work out the details and we saw that you get P2. So what this example is claiming is that if you just do the exact same thing, like the 2 was not special. So you can do the exact same thing that we did with n, and this gives you Pn. And again, if you make n equals 2, it's an example that we worked out together before. Okay, what about weighted projective space? So let's start with positive integers q0 to qn, and let's take them relatively prime. Then let's start with zn plus 1, and let's mod out by the multiples of this particular point in Zn plus 1. Take your Q0, Q1 up to Qn, that gives you a point, it's an integral point, it's a point here in Zn plus 1, then mod out by these multiples of that one. Okay. Now, you have the E sub i's, the canonical vectors in Zn plus 1, take the images of those guys. The images of those guys we are denoting by V sub I. Then, simply by looking at the relation by what we are modding by, if we take Q0 E1 plus Q0, let me erase a little bit. If we take Q0 E0 plus Q1 E1 plus Qn En, that is this guy. So this thing is 0 when you take class. Then this relation is 0. Like this on the quotient is 0 because it's the image of this guy that is what we are modding by. And then we get a fun in this quotient, the tensor with the real numbers, with the same procedure that we did before. It's just that now, rather than having these ones coming from a basis, and this one being minus the sum of the other one, now these guys are just like pointing in any direction. They are still linearly independent over there, and we have this one pointing the other way, but now there can be weights. These QIs are the weights. So, by the same procedure, I meant that the fun is produced by taking the cones generated by all proper subsets of this. So the maximal cones over there would be like this. Omit V0, then is the cone generated by these guys. And omit V1, the cone generated by the other guys, and so on. Those are the maximal ones, and then now faces of those things. So faces of those maximal cones that we just described, it looks just like this one, is now that they can be like somewhat slanted. Because there is like weights in the relation. How do we reconcile it with the example above? Take all the QIs equal 1, and then you see that you get exactly this example. In that case, it gives you Pn. And following some similar argument to what we did for P2, with just a little bit more care because of the weights, one can see that you get weighted projective space with these weights. You'll have to see what definition you use of this weighted projective space. It can be, for example, if you are into that language, Proj of the polynomial ring in n plus 1 variables that is graded by the variable x of I has weight q of I, and then with that definition, one checks that this would hold, or you can use a definition using it as a quotient of projective space, and also with the definition you can check this. Anyway, I just wanted to point out for you that this span for projective space is well understood, and one can check it actually works, and that the same for weighted projective space. Now, then we have this variety. It's a variety that has a torus action. Then for each point, we can see where the action takes it. Then you might remember that we call that the orbit of the point. And then, since we have a group acting, and if the group takes me from here to here, also from there I can go back. Then we have this equivalence relation that decomposes the variety, the topological space is decomposed into some subsets that are disjoint, that are the orbits. And then one can ask, what's the deal here? Do we have infinitely many of those, or infinitely many, which turns out to be the answer? And can we say what they are? Because the philosophy here is that we have some concrete combinatorial object, like this cone. The cone gave me the dual, which gave me the semigroup, which gave me the domain, which gave me the variety. So the cone determines the whole thing. So in theory, any property of the variety, I should be able to read from the cone because the cone determines the whole thing. That in the affine case, and the same in the case of the fan. From the fan, I get the abstract variety. So if I ask, what are the orbits? Well, everything is determined by the fan. So I should be able to say in terms of the fan what the orbits are. And then turns out that the answer is very well understood. There are bijections between, let me start with the second one. The cones in your fan are in bijection with the orbits. And then the procedure that you can use to detect what the orbits are is like number one. There is this definition, this notation. If you take all the union of the cones, you call that the support of the fan. So for example, for the one that we saw before that gave you P2, the support was the whole R2. It's the union of those cones. It covers the whole R2. But I can draw things like you take one cone, the support would just be that. So it doesn't have to be the whole NR in general. Okay, you take limits of the semigroups over here, one parameter, and then I'll clarify over here what happens with those. When you have an orbit, one of these in the line over here, what cone does it correspond to? It corresponds to a cone sigma if and only if when you take the limit over that, when t goes to 0, it lies in the orbit O when your U is in the relative interior of the cone sigma. So when you look at the possible limits of this expression, for U over here, U in the support, so you have your NR, like a copy of Rn. You have all your cones over there. These U's are points in that support. I guess here we should be intersecting this thing with Cn. And then for those we have this, and then you see what the possible limits are. They go to the orbits when you use points in the relative interior of the cone. And then you can say, hey, you never told us what relative interior is. Let me say, is what one would guess it is. For example, if we are in this case of I'm trying to do like a three-dimensional cone. I just did it kind of truncated, but it goes upwards. What will be the relative interior is remove the proper faces. Remove the proper faces, and what you are left with is the relative interior. In this case, it would be this part over here when you have you are able to put like a ball of the corresponding dimension inside. For example, the relative interior, now not of that cone, but of this face over here. This is too thick. This is better now. Okay, see what's the relative interior of this one? I would remove its proper faces. So I would be removing, let me go back, let me removing this one, and I would be removing this one, and I would be removing this one over here. So it would be the yellow part, really, like omitting this ray, and in that one, I cannot have a three-dimensional like a ball, but I can have a two-dimensional one fully contained over there. Like if you think of a hyperplane where this lives, well, look at the span of that one. The affine span of that one, actually the linear span of that one, I can have in that one that is two-dimensional, a two-dimensional ball over here, so that's called the relative interior. So now, there are some nice things about this correspondence. The dimension is related to the dimension of the original cone. We are saying, hey, on your variety with a torus action, there are finitely many orbits in correspondence to the original cones, the cones in your fan. And the size is not crazy. The size fits this. The dimension of your original cone plus the dimension of the orbit that it corresponds to gives you n. Then, for example, when you take the 0 cone, it corresponds to actually the torus. One goes through the procedure to compute the orbit, one actually gets the torus, so it's verifying that at least in that case this is true, and we are claiming it's true always. So, for example, if you have a cone of dimension 1, which we call a ray, the corresponding orbit has dimension n minus 1. And for the maximal cones, as you see below, the maximal cones, meaning I am using the word incorrectly here. It should not say maximal cones because you could have a cone like a fan that like the support is not convex, so maximal cones should not have, do not necessarily have dimension n. So let me say it correctly. N-dimensional cones is what I really mean. N-dimensional cones would then mean that the corresponding orbit has dimension 0. Like if and only if this one is 0, if and only if this one is n. So if you look at your fan and you identify the cones of dimension n, it's telling you like the number of invariant points, of fixed points under the torus action. And then there is also this nice thing over here. You have these orbits. The orbits correspond to the cones, but which ones get in the closure of other ones? Those orbits are not necessarily closed, as one can see in examples. For example, the torus is not closed, it's an open set over there. If I take the torus and I take the closure, well, it's an open set in my variety that is irreducible, so I get the whole thing. So in that particular case, the 0 cone, if I look at the orbit and I close, I get all other orbits. So it seems that at least in that case, it is absorbing the orbits corresponding to cones that are larger than my cone. The claim is that this is true always. If you have one cone contained in another one, then the orbit of the smaller one is in the bigger one, is contained in the closure of the orbit of the other one. So, we have the variety, we have a torus action, then we have a disjoint decomposition into orbits. We understand those orbits, they are in bijection with the cones, and we understand what happens if you take closure of any of them, we see which ones you absorb. And there is more than that, as you will see in a moment. Well, like when you take closures of orbits, it turns out that each orbit closure contains a unique, there is a unique orbit that as closure recovers this one. There is no two sigma 1s and sigma 2 that when I take the orbits and I take, it's easy to see, just a dimension argument, and then you get this. What I'm saying is that there is a bijection also with orbit closures. Orbits and orbit closures are in bijection, one can see. And this is amazing, I think. Each orbit closure is a toric variety, possibly smaller dimension, with a torus of the right size. It's a different torus because this is of a different dimension, but it itself is a toric variety. And then from the beginning, I should have reminded you of something that we said. We started from those cones and got an affine variety. But it is not that this is just one procedure to produce them. All of them arise like that. And the same for the case of fans. If you have an abstract variety that is a toric variety, it comes from a fan. So we describe a procedure to produce them, but the procedure produces them all. What I'm saying over here is that if you take an orbit closure, it is a toric variety, so it comes from some fan, and everything is computable here. So one should be able to describe that fan from the original fan of the variety that you started from. And again, we have variety X. We look at an orbit. We look at its closure. All of this is determined by the original fan, so we should be able to say what is the fan of this orbit closure, granting that this is true. Well, this is how it goes. What is the fan for the orbit closure, orbit of a sigma closed? Well, you do the following. Take the span of your sigma. We use this notation for the linear space that your cone sigma spans. Then now intersect that with the set of lattice points. Well, this is torsion-free, and it's a Z-module distortion-free, so this is free. So we have a null lattice. This n sigma is a null lattice that lives inside our lattice n. Take the inclusion of n sigma in sigma, then take the co-kernel n mod n sigma, and then take dual. And then you see by taking dual that you can identify the dual of this guy just from that sequence. You see that it's identified with a sigma perp intersection m. Like the elements of m are functionals on elements on n. So this makes sense. It makes sense to ask which of these guys give you 0 when you do dot product with your with this guy, or evaluation if you like. If you have not fixed coordinates, it's not dot product, it's just evaluation. Okay, then this makes sense. And as I was saying, just from the sequence that is inclusion of this guy on this guy with this co-kernel, take dual, you see that the dual is of this one is exactly this. Then what you do is the following. Given any cone in sigma, in capital sigma, containing the lowercase sigma that we have fixed, what are we doing again? We have a lowercase sigma, we are taking the corresponding orbit, we are taking closure, we came as a toric variety, we are trying to say what the fan is, then take the cones that contain lowercase sigma. Can be a bunch of them. If my original cone sigma was 0, I will be putting here every single cone in the fan. Then we just look at the images in the quotient. We look at the images in this quotient, but again, we have been tensoring everything with R, just like before. We look at the image of every single cone tau that in our fan that contains little sigma. Just look at the image there. This gives you a new cone over there, gives you a new polyhedral cone, because I just send the generators, and the images of the generators span the cone. Then we have a polyhedral cone over there, it's rational and all. We get a very nice cone over here. One can see it's strictly convex, because if you had linears of space inside it over there, by pulling back, we will have one in the original one, which didn't happen. And then the claim that one can, is not so bad to check, is that they still fit nicely. The cones fit nicely before, then they fit nicely after this projection. And they give you a fan. And then the claim is that one can show that is isomorphic to this variety, and now it's a toric variety because it's the variety associated to some fan. And geometrically, what is happening over here is that you take what is called the star of the cone sigma, which is the set of all cones in the fan containing your fixed cone sigma, and then basically you collapse sigma to a point. What is really happening is that we are quotienting the vector space by the linear space spanned by sigma. So it is like you can think of informally as you are just collapsing sigma to a point, and then what you get is the new fan in this guy. Let's see it with one example. Yes, please. I'm sorry. Yeah.
I don't know if this was, you said something, maybe you proved it already, but you said every toric variety comes from a fan.
Yes, we did not prove that.
Okay.
I give you one word, and then this is like one of the important terms. So it makes the construction very interesting, because if If it was just a particular construction that gives you some toric varieties, well, that's very nice, but it's not the same as actually how nice it is. It gives you all of them. So there is a theorem by the guy Sumihiro that says that when you have like normal varieties with a torus action, then you can cover them by open affines that are T invariant. So then it reduces to show that each, like what I'm saying is like when you have your variety that is normal with this torus action, it allows you to reduce to the affine case. And when you are in the affine case, now you have an affine variety with a torus action, you do this that we were talking about one time. You look at each character, you look at each U in that M corresponding to the torus, and you ask, okay, which of these chi to the U's extend? It gives me a function well defined on the torus, but it's not necessarily well defined if I want to extend from, it gives me a function well defined on C star, I mean, and it's not clear if it extends to the complex numbers or not. Then you ask for which U's it works, and then put those together, that gives you a cone. And then one shows that the toric variety associated to that cone is this precise affine piece. That's how that proof goes.
Is that why we've been having normal in the definition?
Normal,
so the
yes.
construction is like...
Yes, like it is in what I said, you use normality. So with normal, I can get back to this fan picture, but also you need it because every single thing that comes from the fan picture is automatically normal. One can see this, like it is something about the property called saturation. When you take like some semi-groups inside Zn, what you get out of those guys is normal if and only if that semigroup was saturated, meaning when it has some multiple of something, the something was already there, and those are precisely the ones that come from a cone intersected the lattice. So yes, the normality is essential for all of this. Very good. The ones that come from a lattice, from a fan, are normal, and the ones that are normal, I can go back and get them from a fan. Very good. Thanks a lot for asking. Then we are going to see this in one example. It's a subdivision of a cone that we saw before. So in a previous example, we saw, like here is the origin, we saw the cone with the 4 rays that I'm drawing over here. Is these guys, E1, E2, E1 plus E3, and E2 plus E3. We saw that cone before. Let's subdivide it a little bit more by adding this vector over here that is E1 plus E2 plus E3. And then let's see what happens. So let's maybe forget for a second that we started from this one and that we are just subdividing it. Let's start from this one. This is the starting point. But if you're a little bit familiar with this picture of toric varieties, what we have just done over here turns out to be the blow up of the variety that we have before at the invariant point corresponding to the big cone. So there is a correspondence between orbits and the cones. From that cone, that the big one, the corresponding orbit has dimension 0. It gives me an invariant point. If you do this construction called the blow up, you get a new toric variety in this case because you blew up an invariant point. So there is still a torus action. What I'm saying is that it has some fan representation. Turns out to be this one. Anyway, we can forget about that and just pretend that this is the starting point. And then the question is, let's go back and work this out. What is the toric variety structure for the orbit corresponding to the following cone? The red one over there. Let's read what it says here. So we are going to, the corresponding toric variety of this has dimension 3. Again, it's because, for example, start with the cone 0, then you do the procedure, you get the algebra associated to the polynomial ring in 3 variables, localize at the product of the variables. That gives you a 3-dimensional torus that leaves us an open set. Then there you go, it's dimension 3. But in general, these toric varieties end up with dimension n, which is the dimension of the vector space where we are working. Okay, so this one is 3-dimensional. Now let's look at the orbit closure of this ray sigma, the one that I drew in red. This ray in red has a corresponding orbit. Take closure. What dimension does it have? Well, we said that the dimension of the cone and the dimension of the orbit or orbit closure, if you like, because those have the same dimension, those add to 3. And my cone is a ray, so dimension 1. It means that the corresponding orbit closure has dimension 2. So inside my toric variety, I have some that is 3-dimensional. We have some 2-dimensional subvariety that is also a toric variety for a different torus. Then it has its fan. We described in the previous slide what the procedure is, but let's make it concrete. What is it again? So we look at the star of sigma, meaning all the cones containing the red one. So as they are over there, let's try to draw one of those. I guess this one that I'm going to fail at drawing is one of them. You see, that one is one of the many that I need to draw. How many? Turns out it's 9, if I counted correctly. So it's 4 2-dimensional ones contain the red one. And that's the 3-dimensional ones. 2-dimensional ones is also 4 of them. 1, 2, 3, and a 4th over here. And 1-dimensional ones, well, sigma is already 1-dimensional, so the only 1-dimensional thing containing it is itself. So 4 plus 4 plus 1 is 9. Okay, so you have those 9 guys over there. Now, what we said that happens is that we look at the linear span of this guy. And then we mod out by that. We mod out by the linear span of E1 plus E2 plus E3. So you could informally think of projecting here. So we are projecting there and in this direction. And then if you zero out E1 plus E2 plus E3, notice that these two guys add to E1 plus E2 plus E3. And so do these two guys. Moreover, notice that E1 plus E1 and E2, their images generate the image lattice. Yes, because I have the image lattice is in any event an image of the original lattice. So my situation is that I need to be able to produce E1 and E2 and E3 with E1 and E2. No problem. E1 and E2 I produce with E1 and E2, and E3 I produce with E1 and E2 as well because they are to 0. So solve for E3 by sending the other guys to the other side. I'm saying we are declaring this to be 0. So the class of E3 is going to be minus the class of E1 minus the class of E2. So with E1 and E2 I generate the lattice. And what I am saying over here is that notice we have those two guys and their negatives. So what the picture suggests is actually true. What the picture suggests is that when you project, you get this fan. This cone, this cone, this cone, and this cone. You see, I justified by saying I have the images of these two guys over there. They generate the lattice in the image, and additionally, all the rays that I see are those guys and their negatives. So this is what you get in the quotient. And we saw that one before. That one corresponds to P1 cross P1. So then we see, if you have your original variety and you want to look at the structure as a variety of your orbit closure for this sigma, no problem, that's just a P1 cross P1. And then you could do it for all the other orbits closures. We just picked one of them here, but you can do it for all of them and see what you get. Very good. We remarked that this affine toric variety of the original cone before subdividing is singular. We will be doing that very soon. Oh no, did we already do that? Like singular is if and only if. I think it's going to come in a moment. Oh no, we did it. Yes, we did it. Is if and only if you look at the first elements of the race, the first lattice elements of the race, those need to give you part of a Z module basis of n. And this one, if I look at the original one, it has the wrong number to start with. The basis of Z3 have 3 elements. These are too many, these are 4. So it cannot be smooth. It has a singular point for the big one, but notice one can say like where the singularities are, because we have the 3-dimensional cone. I am ignoring the red one for a moment. I'm talking about the original one. The original one is 3-dimensional. You have the corresponding invariant varieties. You have the corresponding point to the whole cone. That one we just said why it is a singular point is because this is what happens. These guys give me a big cone that is a singular cone, but if I take this other fan, look at this, take the fan, that would be ignore everything inside. What color could be good for that? In purple, remove all of this inside. So take inside R3 a fan that just consists of 0-dimensional cones, 1-dimensional cones, and 2-dimensional cones, no 3-dimensional cones. Those should be all non-singular. So you have this, and what is it missing? This is kind of cool. What is it missing from the variety if I don't erase the purple? It's really missing 1 point. Because we have this fan, you can apply this picture of the corresponding orbits. What am I missing? I'm only missing 1 orbit that comes from this big cone in purple, and that one is 0-dimensional, is 1 point. So by removing all of this here and taking the fan that is all of the cones except that one, I only removed 1 point. And that one is non-singular anyway. So what happened over here is that we have an affine variety that is singular, and is singular at exactly 1 point, the T invariant point corresponding to this big purple cone. Now we subdivided it, and then one can apply this criterion that I just reminded you of looking at the primitive generators of the rays, the first point, that is lattice point on the ray, put those together and ask if it is a part of a basis for the lattice. For this one, the subdivided one, it is true. Like take any, let me erase the purple. If you do it for this one, for each single cone, that works. The primitive generators of every single cone, put them together, that can be extended to a basis of the lattice. Then that one is non-singular, and this is what one would call a resolution of singularities. One can see that this map is like proper, and one can see we started from the original one. We have a proper map from one that is non-singular, and they are birational. Like they have an open set in common that the map restricts to an isomorphism. This is a resolution of singularities, and just one comment is that this is not the easiest way to resolve the singularity. So we started from the singular cone. We produce another variety that is almost like that one. Is that you replace a point by a copy of P1 cross P1. That's what happened. We started from a singular variety that is singular at only 1 point. We added this ray sigma. That point got replaced by a copy of P1 cross P1, and the new one is non-singular. They are isomorphic out of that. If you remove the point on this side and you remove the P1 cross P1 on the other one, they are equal. That's what we changed. A point for a P1 cross P1, we passed from a singular one to a non-singular one. It's a resolution of singularities. And one cool thing is that one can work out resolution of singularities for toric varieties in any characteristic. That's easy and well known. What we are saying over here is that there was an easier way. I can just comment very briefly. If instead of taking these 4 extra cones over here, imagine that we put these 2 together, these 2 3-dimensional cones, put them together. And these 2-dimensional cones, put them together, and then you don't need the ray sigma anymore. It's not doing anything at all. I cannot leave it there because it would not intersect the remaining cones on a face anymore. So we remove, we identify these two, and remove sigma. That gives you a simpler fan that also is non-singular. That's what this comment is trying to say. There are other ways here to resolve the singularity that are easier. Anyway, that was just a comment.
Oh, so
Yes, please.
question, sorry, you mentioned. So, in this example in particular, you're subdividing, instead of adding the central ray, you're subdividing by
Yes.
like an edge, right? But you can do it this way.
You can do it the other way as well.
It's going to be like a flip.
Exactly. That would be an example of a flip. Very good. Yes, thank you for pointing this out. Thanks a lot. Yeah, he's just pointing out that I made a choice here. Like, we took this three-dimensional cone found by these guys, and then we added like a wall in this direction. And he's pointing out we could have done it the other way. And that's fine, and those two, yes. And there is a name in algebraic geometry for the operation of passing from one of those to the other. Do you have a question over there?
Yeah. Can you see what is actually the orbit, not the closure, but the orbit?
Yes, these orbits are all well understood. They are actually tori of smaller sizes. They are when one works out the correspondence from before, while working out the proof, what you see is that each of these orbits looks like for example, the big one is a copy of C star to the dimension, and the other ones are that as well, but for smaller. Yes. A very good thing you were asking. Yeah, like we describe the structure of the. It's an excellent question. Like we describe the structure of toric variety of the orbit closure. Actually, the orbit is the torus of that one. So it's a torus, and it's the torus of the orbit closure as a toric variety. Yeah, very good. Thank you for asking. It's a very good point. It's a torus, and it's the torus of the toric variety that is the orbit closure. Yes, please.
Is there a map between this subdivided toric variety and P1 cross P1? What's it afterwards?
A map between this one and the P1 cross P1, I am not sure if in general, because that would be like asking if I have a variety and I do a blow up, if I have a map in general from my variety to the exceptional divisor. And I feel maybe in general we don't have that.
I guess what I mean is there a map between a toric variety and the toric variety that you get from the toric variety of any of its like orbit closures?
Some retraction, like for example, you're saying if I have my X and I take some orbit closure, then I have one over here, do I have a retraction there? And maybe, yeah, it is related to what I was saying. I am not sure because, for example, like if it was through if some statement that we take out of the toric world, it would allow me to do what I was saying, like, because this is an instance of that. Here in this particular case, it's like the exceptional of divisor of a blow up. So in general, I cannot do that type of thing. I don't know if in this special setting I had that. Like a retraction from like my variety to these orbit closures, I'm not sure, maybe, but I don't know. Thank you. Thank you for asking. So now some properties of toric varieties that in case you're not familiar with these words, I'm going to say a little bit about, I'm not going to give the formal definitions, but maybe give an intuition of what the notions mean. Some properties of these varieties, of toric varieties, just arising from some funds. If we have a toric variety determined by a fund sigma in NR, then the variety is complete. If you know those words, that really means the map to a point is something called like proper. So then it is separated, finite type, and universally closed, whatever that means. But over the complex numbers, you can see that your affine pieces live inside Cn. So it makes sense to give them the topology of the complex numbers to the n. And then it makes sense to give the variety this topology coming from the complex numbers to the n locally, and those fit to a complex topology on your object. In that particular case, this word complete just means being compact. So think, if you care only like about the complex picture, we can say when the toric variety is compact. It's compact if and only if your sigma is what is called complete. What is that? Is that your cones cover the whole space where you started from. So if I start here and my cones say look like this one, and this one, it is not complete because I am missing this part over here. That's what we are saying, that when the fan, you put the cones together, you cover the whole vector space where we are working, then the corresponding variety is compact if you consider like the complex topology. It's if and only if. So in this case, you would be saying that adding this one over here would make it compact. And it's funny because we just added 1 point over there, using again this correspondence between the cones and the orbits. What is the orbit that we are missing? So if we are not adding this one in red, I have all the same orbits except one. And that orbit is one-dimensional because the cone is two-dimensional and the dimensions are 2. So it's just missing 1 point. So if I consider the whole fan in this example is P1 cross P1, that removing this red one is just removing 1 point. So yeah, I guess you see, oh yeah, it's not compact. But with this one here is P1 cross P1, it's compact. And what we are saying is that this is not a coincidence, it's true always, is you get a variety that is compact with the complex topology if and only if your fan covers the whole thing. Maybe I lied and I didn't give this definition before. No, I think I did. So for a cone, we gave it. And then you can see that it translates to the fan as well. So your variety is smooth. Well, I can see that my variety is smooth when I cover it by affines, and each of those is a smooth affine variety. It will be if and only if. You can check this locally. It's a local property. So what we are saying is that the criterion that we gave is just, we can read it off and translate it over here. A variety is smooth if and only if every single cone is smooth. What was that again? Is that if you look at the generators, the minimum set of generators, meaning you look at the rays of that cone, since it is rational, it makes sense to intersect with the lattice and consider the unique generator of the ray intersected the lattice. This one would be over here, this one would be over here, and this one would be over here. The assumption is that these guys are part of a Z basis, of a Z module basis of your lattice. And that's if and only if the particular affine patch is smooth, but if you ask for this for each cone, well, then your variety would be covered by smooth open affines, then the whole variety would be smooth. And I remind you that we saw that when you have this assumption, it is indeed smooth. Like one of these directions we basically saw is one of the examples from before, because we saw that in that case, the corresponding variety was a product of copies of the complex numbers with copies of the complex numbers with the origin removed. The next property, let me not define it, but is that the toric variety is Cohen-Macaulay. This happens always. And the last property over here that we are listing is that it has what is called like rational singularities. This is basically that you have a certain resolution for which there is something called the structure shift. When you do the higher direct images, those are 0. That's the definition, but that is just very convenient when you work with these ones. And then let me move on, but let's just think about these ones again for a second. Properties of toric varieties. Then we understand when they are compact, is that the fan covers the whole area. We understand when they are smooth, is that you look at the cones, you look at the minimum generating set, is part of a Z basis of the lattice. They are always Cohen-Macaulay, and then they always have this property that is like very helpful, which is called like rational singularities, which is something about having a resolution with a certain property, but then it means that for any resolution it would hold as well. Very good. So let me make a small jump over here, and I'm going to jump here. Okay. So now I'm going to talk to you about simplicial toric varieties. We gave this definition of simplicial before for a cone, but for a fan would be that each cone is simplicial. And do you guys like it there like that? I'm not sure. I don't know what's easier to see. Anyway, so we're talking about these simplicial cones before. A simplicial cone is generated by as many vectors as its dimension. For example, a cone in 3 dimensions generated by 3 vectors like this is simplicial, but a cone generated by 4 vectors, say like this, would not be simplicial. In dimension 2, automatically for free, every cone is simplicial. If it is 0-dimensional, it's just generated by nothing. If it is 1-dimensional, it's just generated by 1 point that is non-zero over there. And if it is 2-dimensional, well, in dimension 2, I don't have many choices. In dimension 2, there are just 2 extremal arrays, so it's simplicial for free. So in dimension 2, everything is simplicial, and now we start seeing non-simplicial cones in dimension 3, and then again, a fan would be simplicial with when every single cone is. Then I remind you of this definition, or present it to you for the first time if you have not seen it before, is something about singularities. A point in a variety is a finite quotient singularity if you have a finite subgroup of the invertible matrices over the complex numbers, so that your point, an analytic neighborhood of your point, looks like quotienting this affine space by the action of that group, where the action is used by multiplication by these invertible matrices. We have a group of invertible matrices of the correct size to act on Cn. Since this is a finite group, this quotient exists as a variety. If you want, you just take the ring of invariance of the polynomial ring in n variables. It is well known that this is finally generated. This is a domain. Then you can look at the corresponding affine variety. That one is this quotient. So if P on X looks like 0 on this quotient, then we say that it's a finite quotient singularity. And then again, the word analytically over here means that we have neighborhoods in the complex topology such that you have a bijection that is given in both directions by convergent power series. And then, I was reminding you of this before, a rational polyhedral cone is simplicial if the minimal set of generators is linearly independent over the real numbers. Equivalently, you can generate it with as many elements as its dimension. But this is also a very nice way to think about it. The generators, it can be generated by a linearly independent set. Because there might be other generating sets for the same cone that are not linearly independent, because once you have a generating set, you can throw a bunch of other things and you still generate. What this is saying is if you can generate it by linearly independent elements, it is simplicial. Then the main result concerning simplicial toric varieties is as follows: that when you have a toric variety, then the following things are equivalent. Your variety is simplicial if and only if it has finite quotient singularities, which people also use the word quasi-smooth for that. It's a synonym. So this definition that we gave over here, that the singularities are not too bad, they can be seen as you take the affine space, act by this finite group, and look at the 0 in that quotient. It is sometimes, depending on this G, can be because you can take G trivial, so it's non-singular. But if you take other G's, this can be a singular point. If your variety, the point looks like that analytically, you call it a finite quotient singularity, and then the variety is simplicial, meaning your cones are generated by linearly independent rays if and only if your variety doesn't have these bad singularities, just like finite quotient singularities. All the singularities are like this, not so bad. Then one could say the main result concerning simplicial toric varieties is as follows. Yeah, nice, but like if you ask me, like I would put another one over there. I like it, I use it much more. I use these ones, like simplicial toric varieties have this property. If you have heard of divisors, there are two types of divisors. There are veil divisors and Cartier divisors. And Cartier divisors, like veil divisors, we're going to see them in a moment, is just basically a sum of invariants of, not invariant, of subvarieties of codimension 1 with integer coefficients. And they locally do not need to be given by a single equation. When they are locally given by a single equation, you call them Cartier. And what happens over here is that on a simplicial one, every single veil divisor, just a formal sum of subvarieties of codimension 1, is always locally given by one equation. That's not true. A multiple of it satisfies that. Let me say that again. Every veil divisor has a positive multiple that becomes Cartier, meaning is locally given by one equation. I use that every day. Anyway. I mean, not just for toric varieties. That's a property very important in algebraic geometry. It's called Q factorial, very important to me, and simplicial toric varieties have that. So many times when you write something using toric varieties, many times you work out the simplicial case first, and then reduce to that one, or you work out the smooth case first, and then see how to prove the general case from that one. Sometimes I have done things that you first prove the smooth case, then prove the simplicial case, then prove the general case. Yes.
So it's actually simplicial if it's Q factorial, but
if and only if. Yes, thank you, because I said it and I didn't make it precise. A toric variety is simplicial if and only if it's Q factorial. Q factorial, again, veil divisors have a positive multiple that is locally given by one equation, so it's like Cartier divisor. And some of you guys might work a lot with divisors, then that comment, yes, hopefully is helpful. Then let's look at one example over here. Let's take a complete fan in R2. So these are two examples of that. In fact, two examples. Sigma is a complete fan. So this could be sigma. It's a very poorly drawn sigma. Let me draw it again. But this could be sigma as well. These are just two possible examples of sigma. And actually, for a side comment, one of them is obtained by adding this ray to the other one and subdividing. Turns out that corresponds to a blow up. This one actually corresponds to this quadric cone over here, and this would be a blow up of that point. Anyway, that's just a side comment. The point is that out of either of these two, you get a surface that is compact because the cones cover the whole R2. It's some compact surface. If you work over fields, I guess we'll just be saying it's complete. One can see that it is actually projective. We'll get to that hopefully very soon. And there is this observation that we were making before. The cones are, the bigger cones are two-dimensional. Those are automatically simplicial. I mean, they are generated by the two rays that are distinct, so those are linearly independent. So those are simplicial. So then it has finite quotient singularities. Furthermore, if you erase the two-dimensional ones, we are just removing a couple of points. Now it is smooth. If you remove those 4 points in this one, well, this one is actually smooth. I don't need to remove anything. But something that is easier to see with fewer computations is that if I remove these 4 cones, so your fan is only the origin and these 4 rays, that one is smooth with no work at all. Because you see, 0 by itself satisfies the definition of smooth. It actually gives you the open subset that corresponds to it is the torus, as smooth as it gets. And these ones over here are smooth because you take the very first lattice point over there, and that can always be extended to a basis of Z2. If you take any vector that the 2 entries are relatively prime, you can always complete that to a basis of Z2. So what we have over here is that we get some smooth thing with possible singularities at 4 points, but one can check the criterion for smoothness, and you check that these 4 points in this particular example are actually smooth points, but not in this case. In this other one here, if we only take these ones and the origin, is smooth for the same reason, like 0 in an event gives me something smooth, the rays in any event give me something smooth. The danger is now the two-dimensional ones that are in any event finite quotient singularities, but they could be not smooth, so one checks, and this one is smooth, this one is smooth, but this one is not smooth, but it's still a finite quotient singularity. And then it is resolved by adding this subdivision here, that what it did is just add this guy over here instead of this point. Okay, let me.
Sorry, another question. So in this example and in the other one of the three-dimensional cone, what you are adding, I'm guessing, is since that cone is not like you need more generators aside from the rays, you are adding overseeing. You are adding that generator.
Yes, like let me see if this zooms in, and maybe you can see. Yes, that's a good point over there. Oops, let me erase this stuff. You guys see a zoomed in version. So if we look at this cone, and I have this guy, I have this guy, but this one in red is problematic. I cannot get it with those. So we add that one. With this one, I need. I cannot produce that point with the other lattice points. I could even add all of the other lattice points. I don't get that red one, even adding everything else. So that one needs to be added as a generator. But after you add like a subdivision through that one, now both of these, I can get every single lattice point. In this cone, I get every single lattice point with these two. And the same in this one. In this cone, I get every single lattice point with these two. So that one can see now that it's non-singular after we did that subdivision. And then it says over here now that each one is something that I told you. Each one-dimensional cone is smooth, like always, because it is generated by a primitive element, meaning an element that you don't have a common integer that divides the coordinates. So it's not of the form some other points times L. So it's generated by one of those, and that can be completed to a basis of Z2. So these one-dimensional cones are smooth, and then the singularities can be just happen at some points, and it's like the points for which the corresponding cone is not smooth. For the one that we have drawn, would be the only bad one is this one. This gives us a singular point, and everywhere else that variety is smooth, and this one is all completely smooth. Very good. So let's discuss this about changing the lattice. So let's start with a lattice n, and let's take a sublattice inside n prime. And let's not take it very tiny. Let's take it such that each vector in n, which is point in the lattice n, when it takes some multiple, it gets in this one. So it's like a finite index sublattice. So this one has the same dimension. Like, for example, inside Z2, imagine taking the points so that every coordinate is even. That gives you a smaller lattice inside the bigger one, and that can be, for example, the example to keep in mind of your n prime.
And that would be index what form?
Yes. Very good. Then, if we tensor with R, you just get the same thing. So it's the same R2, but we are considering to Z2, and then some subset of Z2 that is still a lattice of rank 2. And then make it n if you like. Okay. And one can verify directly that if in this Rn you have a cone that satisfies the polyhedrality condition, then it's polyhedral with respect to either of them, because you just find generation by finitely many vectors. Rationality is also the same, because you are free to scale by positive numbers your generators. So rationality works as well, and it is easy to see that you still get a strongly convex, because if it is in one version, it is in the other. That's somewhat clear. So you have a strongly convex rational polyhedral cone on both, on NR and N prime R. Then out of that, we get affine varieties, affine toric varieties. We get one following the procedure inside N, and we get one following the procedure in N prime. Then let's keep the N and N prime in the notation because we usually omit them because the N is fixed for the picture, but here we have two different lattices, so we need to keep the N in the notation. So this is V sigma N and V sigma N prime is the toric varieties constructed with the same procedure that we did before. And then over here, M prime is just what we did before with M, but just done with N prime. So it's the dual lattice to N prime. So the notation was the usual one. N is the lattice that we start from. M is dual. We have this other lattice M prime, N prime. M prime is its dual. So this is the construction that we reviewed at the beginning of this lecture. Then we have an inclusion of these two guys, one can see. Like these N and N prime were included in one direction when it's easier to see if you choose coordinates. Choose coordinates for this guy and then see that this one, like there is this fundamental theorem for finite abelian groups, finely generated abelian groups. And then one can see that this one, you can choose a basis of this guy so that this guy looks like those elements scaled by certain positive integers. And then using that, maybe this is easy to see. Then if this guy M can be seen as a sub-lattice of this one, then we can intersect sigma dual with both. So we get an inclusion between sigma dual intersected M to sigma dual intersected N. But if I have that inclusion of the semigroups, that gives me an inclusion of the semigroup algebras, and then I get a morphism of the toric varieties, but in the other direction. So I get this map over here, it's a morphism, and let's remember that it goes in this direction. So from the smaller one to this bigger one, from the variety associated to the smaller one to the variety associated to the bigger one. At the level of tori, one can see that this is just the map, that is the inclusion of this tori that comes from here. Why do we have such thing? Is because those tori, one can think of them as tensoring with C star. Tensor C star. So just tensor that inclusion with that C star and you are fine over there. Then, well, it is not injective anymore. Tensoring breaks injectivity, but one can work out what the kernel is. So it is, we get at least a map. You just get the map by tensoring this inclusion with C star. It does not stay injective. And this is the claim. The claim is that you can work out what the kernel of that map is. The kernel is isomorphic to N mod N prime. We can discuss it after the lecture. It's a nice exercise using just Tor 1. I don't know if you guys have an easier way to see it, but one just uses a little bit of Tor, and then you see that you take basically just like the inclusion, take the co-kernel, and then tensor with C prime, and then compute what the Tor 1 has to be, like a Tor 1 that goes one step further in the exact sequence, and then you get that the kernel of this is exactly N mod N prime. Anyway, then what have we said? That we have a copy of this guy, N mod N prime, inside this one, because it's just the kernel of the map. We have a copy of this one over there. Then in particular, if I have an action of a group G on something, and if I have a subgroup, I also have an action of the subgroup. Which action? The same. Just do the same thing. Okay, then we have an action of G on this variety where this one acted. And then the claim is that one can compute the invariance. Part of this is done in the notes. I'm not doing it here. That one can compute and see that this is the quotient. What would you need to do to verify this? Look locally at the invariance by this. Because these quotients are defined by the affine variety associated to the subring of invariance under the action of G of the coordinate ring of this one. You know what the coordinate ring of this one is, you know what the action of G is, check that, and also you know what this one is, so just checking that the invariance would be precisely the ones that are these guys. Very good. So what do I want to say now? So what we have just said that if you have a sub-lattice M prime and I keep my same cones, that's how you would apply this type of thing. You have one of the lattices, you have the cones, we are going to change the lattice. We consider a different lattice and one wants to see what happens to the variety. What we have said over here is, hey, you just got a quotient. Quotient by what? By the quotient group of these two. The variety just got quotiented by, well, like the one for this smaller one got quotiented by the group that is the quotient of the lattices, giving you the variety with respect to the other lattice. We did it for a cone, but this construction would be compatible if you do it for all the cones. What are we saying? That for the whole variety it happens as well. For the whole, so if you have a fan and you look at that fan in both N in R and N prime R, do the quotient patch by patch, you get a quotient for the whole variety, and what we are saying is that the variety that you get working with respect to the smaller lattice admits a quotient by the group that is the quotient of the lattices, and that quotient is the variety that you get with respect to the bigger lattice. Let's see it in one example. We have talked about weighted projective space. We said that we fix some weights relatively prime. They are integers that are relatively prime. And over there, the V0 to Vn were the images of the canonical vectors in this quotient. So inside this lattice N, we said we have this relation. We have that Q0 V0 plus Q1 V1 plus Qn Vn is 0. But then let's give names to these guys. These guys, let's make them the W's, W0, W1, Wn, and then let's consider there are too many to be the basis of a lattice, but they still generate some lattice. They generate some subgroup of Zn, of a copy of something isomorphic to Zn, distortion free then over the integer, so it's free, and one can see it has finite index. Then we are in the situation from before. What I'm saying is now consider the Wi's. It's basically absorbing the weight into the vector. We have some weights applied to the vectors, rename the situation. Instead of Vi's, now take the Vi's times the weight and call those Wi's. What we see is that now the W's with no weight at all give you 0. So this reminds us of something. This reminds us of what we use to construct projective space. It's just what we did over there. So the W's add like this, they have this behavior, and they form a Z basis of M prime, one can check, and then it follows that if you work with N prime and the W's, you just get Pn. If you work on N, is our construction that we gave of weighted projective space. So this up here is saying that Pn admits a quotient by the finite group that would be the quotient of N and N prime with quotient variety equal to weighted projective space. So weighted projective space can be presented as a quotient of the usual projective space. Yes?
Quick question about 2.2. So it seems like a priori you're making the assumption that that variety modeled by the orbits is already a toric variety. And then you're saying there's an isomorphism to this other toric variety. But
I-
in general, if you quotient by orbits, you don't get something in the same.
Yeah, exactly.
category.
Yes. So that's the claim that we are making over here, that what you get is this toric variety. But the proof is not.
But why is it a toric variety to begin with?
So this is the situation.
I
Part
think
of the
that
proof.
has to do with G, right?
Yes. So I skipped a little bit of section 2.5, and then you can in the notes of David Cox, and then you can see a little bit of how it is done. But this is the situation. This is like we can see it here. What do we need to check? So over here, the one on the right-hand side is a toric variety. Like I have two toric varieties, and then the claim is that those two toric varieties are related like this. But what is that really saying? These quotients are constructed, like there is like this geometric invariant theory is constructed by, you look at the coordinate ring, you look at the subring of invariance, and the quotient is like the variety associated to that subring of invariance.
But that has to be finitely generated.
Yes, it is here. Yes, and not just it is finally generated here, we see what it is. Like this is a very concrete action. So the claim is that when you look at the action on this guy, the invariants are these ones. These two are two concrete things. So we have the sigma presented in one and the other, and we have the action. The claim is that this is the subring of invariance for this action on this guy. That's what we need to check. And in the notes of David Cox, he wrote a little bit more about this. I omitted a little bit of that computation, but there is more over there. It would be in section 2.5. I'm working here now, section 2.7. If you go to a little bit earlier, he works it out in one case, and it works just like the general case. But thank you for pointing this out. Yes, like for free, if I take a quotient, it will not be a toric variety. But we're saying that the situation is very concrete, and one can see that when you look at the invariance of this ring under the action, you get actually this one. So then you see that you get a toric variety in this case. Thank you. Then now, let's start a little bit in the last few moments that we have, the next section. This one talks about something called homogeneous coordinates and something called toric ideals. Because up to now, we gave one construction of toric varieties. We said, out of a cone, I get the affine ones. Out of a fan, I get all of them. A cone in particular is a type of fan. Well, a cone and its faces is a type of fan. Then there are several methods to construct them. There are at least two more that are like very well known, and then we can say a word about those during the next maybe next lecture. We can start saying something today. One of them is this generalized homogeneous coordinates, and then there is the other method called toric ideals. Maybe we'll say a little bit about each of those methods. But before we do that, to illustrate this point that on toric varieties you can compute things, let's compute something that maybe some people with interest in algebraic geometry, and maybe it also shows up a lot in commutative algebra, is these divisors. So I'll introduce to you or remind some of you about this notion of a veiled divisor on a normal variety, and then I would like to point out that if you are an commutative algebra enthusiast, this word you don't need. Like our reference would be the book of Fulton. He works out without the normality assumption, but if you have normality, things are much simpler. If you have a normal variety, it's not needed for the definition and it's not even needed for the results. A divisor is just 7 times this subvariety of codimension 1 minus 12 times the one over there plus 15 times the one over there minus 20 times this other codimension 1 subvariety. It's just a formal combination with integer coefficients of codimension 1 subvarieties. Very good. So you could say is the free abelian group generated by all codimension 1 subvarieties. We call that a veiled divisor. You need to use an adjective over there because there is some other types of divisors. I was mentioning a moment ago a Cartier divisor. Okay. So in a toric variety, you can compute these guys. Well, even more than that. Let me just continue. given a non-zero rational function, so you have a function that is a regular function on some non-empty open set of your variety, and is not the zero function. This is the nice thing about normality over here, that we can define easily, is not needed, but with normality is easy, to define the order of vanishing, or of the pole also, of this f along a codimension 1 subvariety x. Because if you look at the local ring, it's a one-dimensional domain that is integrally closed and is local. Local one-dimensional domain that is integrally closed, so you get a DVR over there. So you use that valuation to produce integers, which intuitively mean to you, because this is basically in which power of the maximal ideal of that local ring you get, is telling you the order of vanishing over there, or if you get something negative, would be the order of the pole along that particular codimension 1 subvariety. Then, if you do this f along every single codimension 1 subvariety, out of each one you get an integer. Put all of those together. It gives you a formal combination of your y's. And you could think, oh, but like that could be an infinite sum, and you're only allowed finite sums. Oh, no problem. Because if you look at where the function f is regular somewhere, and I remove the proper closed set where it is 0, so I end up with a small, not as small, it's dense, an open set where f is regular and non-zero, so 1 over f is also regular. So f and 1 over f is invertible in some place, and then one can easily check that gives you that this order of vanishings are then 0. So what I said, and then this is the other thing, if you have an open set inside a variety, the complement is a closed set of dimensionless, so it has finitely many components. So what I'm saying is, all the components that intersect a certain open set that I fixed, the order of vanishing is 0. So in any event, there are at most finitely many of these guys non-zero. So you get a well-defined divisor. And then we are going to define that two veil divisors, are linearly equivalent if the difference of those guys is of this form. The divisors of that form are called principal divisors. And if we take all veil divisors and we mod out by principal divisors, you get what is called the class group of your variety, which, following the notes, is also the Chow group of size n-1, where the n-1 comes from the dimension of these varieties that we are looking at. These divisors have dimension n-1. There is some concept of Chow groups. This is the Chow group n-1. And then the idea is that we are next going to see that on toric varieties we can compute this very easily. This is the class group. We can compute the class group easily on a toric variety. It also happens to be the Chow group n-1. The point is, we can compute this just from the data of the fan very easily. But it is 11 a.m., so that's all for today. Thanks a lot for your attention.
Are there questions or remarks, Professor?
Yes, please.
Your last definition is not more usual to take, since you are taking veil divisors, modular or linear equivalence, so you actually have dimension 1 cycles, right?
Yes.
So this means that you are taking an-1 of x, that means a upper subscript, not lower subscript, because lower subscript is more for homology.
I am doing the homology one, yes. I think I'm using...
You already have the Chow group. You can work with the a-1, that means cycles in dimension 1, because you have divisors, modular linear equivalence.
Let me think for a second. Yes, you are right. I'm sorry. So I took this from the notes. Yes, of course. So, yes, you are right. Let me... No, never mind. let me take that back. No, this is fine. Because, like, this is
The
the,
intersection ring, you have dimension 1 cycles, right?
yes,
Modular linear equations.
yes.
So when you take this, you have the A1x,
Yes, so,
but upper subscript, not lower subscript.
so like,
Because lower subscript is reserved for homology.
so I think that following just Fulton's notation, so for the groups is you start from like so K, you start with dimension K things. You start with dimension K cycles, and then you go and take like dimension K plus 1 things and normalize, and you take some divs over there and you push forward those guys, but in any event, is indexed by the size of the thing. Like the Kth ones with lower index comes from cycles of dimension K. So that this one is consistent with Fulton's book. And if I put them upwards, which I cannot because these are not smooth, but say that I was lucky enough to be working with something smooth, I could go upwards, and then this would be, if my thing was smooth, this would be upwards 1, but I don't in general have the upwards because the upwards are, unless I was meaning, say, like operational, chow. I have upwards in the case of smooth, unless I'm meaning the operational version. In any case, I think that this is consistent with Fulton's book. We can talk about it, but my impression is that this is fine. I mean, anyway.
Is there any concept of the toric subvariety? And in that case, can you characterize all the toric subvarieties of toric varieties?
I think this should be. Let me think. I don't know if the answer will be just like that is what we have, because yeah, like if I was just yes, the answer will be yes, and then I think we understood it, and I think it just follows from what we did. If the definition is my first guess of how one could interpret that, because if I was going to call something a toric subvariety, I would like it to be that this inclusion is compatible with this action, so it's invariant or the action of T. But the invariant subvarieties are, you can read them all from the fan. They are precisely in correspondence to the cones. And then they are all, the toric structure is the one that we gave by projecting the star. So then the answer is yes, we understand all of those directly from the fan. There will be a correspondence with the cones, and we can even say what the toric structure is just by projecting the stars on the space that is the perp of the span of the cone.
Other questions?
Yes, please.
It was about when you showed the fans associated to the projective spaces. They were given by all the subsets of a certain set.
Yes.
Proper subset. That's a simplicial sphere. Is there any characterization for fans which have a simplicial structure in that sense?
So let me see if I understand. Like looking at ones that have that form, like n plus 1 in dimension n plus 1 rays, that any n of them span Rn. If that is the ones that you are asking about, all of those are precisely the weighted projective planes. And I don't know if I understood that those are the ones that you would be asking about. Like that structure, having n plus 1 raised in Rn, so that any n of them span the vector space, one could see that that's precisely the... Or you're meaning some different ones. Could you please clarify which ones you're asking about? Thank you.
Yes, when we define the fans of the projective spaces, they were given by a certain structure.
See, let me see if I then understand now. Like when you look kind of in the sphere to see things that would be like all simplicial. Oh, then now that would be, yes, it would be too big of a collection of varieties. Pretty much everything. Every Q factorial toric variety would arise like that. Very good, thank you.
Okay, so if there are no more questions, there is an announcement. So we are gonna have another group picture right now. same spot as last week, okay? And so let's thank you, Jose, again for his lecture.